Go over some max min type problems, or optimization type problems. In this example, a gardener wishes to use 400 feet of fence to enclose a rectangular area, a rectangular garden on 3 sides. The other side is bounded by a river. Assume the river runs close to a straight line. What is the maximum area? So here we have the river up here, and we want a fence to enclose the rectangular area, and and we want to know the maximum area, but it'll also help to know the dimensions here. So we can call this side W, and it's a rectangle, so the opposite side will be W, and this other side is going to be 200 minus 400 minus 2W, because we have 400 feet of fence altogether, and we're subtracting the two other sides. So so the area is going to be the length times the width. We don't know which of these is the length and which is the width, but anyway, this is going to be 400 minus 2W times W. It doesn't really matter which one is the width and which one is the length. And if we distribute the W on the outside, we're going to have A as a function of W is going to be 400W minus 2W squared. And then, so then we can take the derivative. A prime of W is 400. So this area function is the function we're trying to maximize. And then the exponent comes out in front. 2 times 2 is 4, so it's 400 minus 4W. And the maximum, okay, actually we need a little bit more here. So the width, W has to be greater than or equal to 0. We don't know if it's the width or the length, but W has to be, because width and length are both positive. So W has to be greater than or equal to 0, and 400 minus 2W has to be greater than or equal to 0. Probably should have done that first. If we solve this for W, add 2W to both sides, we get 400 greater than or equal to 2W, and then divide by 2. That gives us 200 greater than or equal to W. So we have W greater than or equal to 0 and 200 greater than or equal to W. So that we can write this, if we write these from smallest to largest, we have 0 less than or equal to W less than or equal to 200. Okay, so it's yeah, if the width is equal to 0, we have a kind of a degenerate rectangle. So I'm going to include 0 there, but really it should be greater than 0. But we're going to say it's the width is greater than or equal to 0, and the length is greater than or equal to 0. Okay, so so let's go back to this derivative again. We said a prime of x, a prime of W is equal to 400 minus 4W. So so the maximum area is going to occur either at one of these endpoints at 0 or 200, or it's going to occur at a critical number where the derivative is 0 or undefined. So we want to set this equal to 0 and solve for W. That means that 400 is equal to 4W. If we add 4W to both sides, divide by 4, and you get W is equal to 100. So so the critical number is 100. That will make the derivative 0. And then we have the two endpoints, 0 and 200. So if we evaluate W at each of those values, evaluate the area for W equal each of those values. So area is equal to 400W minus 2W squared. So it's going to be, if you put in 0 here, we get 0. Put in 100, 400 times 100 minus 2 times 100 squared. 4 times 1 is 4, and you had 4 zeros there, so it's going to be 4 followed by 4 zeros. And this 100 squared, 1 squared is 1, and you have 4 zeros there. So 1 followed by 4 zeros, then you multiply by 2. So 2 followed by 4 zeros. So it's 20,000. And subtract, you get 20,000. And if we put in 200, if W is 200, you have 400 times 200 minus 2 times 200 squared. 4 times 2 is 8, and you have 4 zeros. 2 squared is 4, and then times 2 is 8. And when you square it, you double the number of zeros, so you have 4 zeros there. So this is equal to 0 also. So we have the minimum area occurs at the two endpoints, and the max is in the middle. So this is the min, max, and min. So we want the maximum area, which is would be 20,000 square feet, and that occurs when you have W is 100, and then the 400 minus 2W is going to be 200. So the that occurs if you have W equal 100 feet here, and then the other side here, 400 minus 2W, 2 times 100 is 200, so that's equal to 200 feet. So that's those are the dimensions that will give us the maximum area. And that concludes this presentation.